Okay, last part of chapter 6. We've been talking about the periodic table. We've talked about all the families on the periodic table. We talked about the properties of those families. The last thing that we need to do is cover a few what we call periodic trends, right? So there are some properties that change on a pretty regular basis as you go across the periodic table and as you go down the periodic table. And we want to go over some of those because those are going to be important as we go forward, talking about these elements coming together later on to bond with each other and make different compounds. The first of those trends is about atomic radii, okay, or the size of the atoms, in other words. So if you take the periodic table and you look at the size of the atoms of the different elements in the periodic table, it turns out that as you go across the periodic table, the size of the atoms gets smaller, and as you go down, the atomic radius increases. Okay? So that means that the biggest of the atoms are going to be down here in the left corner of the periodic table, and the smallest ones are going to be up here in the right-hand corner. So you need to know what the trend is each way. Okay? It increases as you go down a group. It decreases as you go across. But also, and maybe even more importantly, you need to know why. Right? And there's a couple of really simple reasons why this happens. And we'll cover the easiest one first. As you go down the groups on the periodic table, the atoms get bigger and bigger here because the number of shells, the number of energy levels is increasing. I mean, think about it. Hydrogen has a 1s. That's it. It's the only electrons that are filling any of the energy levels. But lithium has a 1s and a 2s. Sodium goes up to 3s, potassium goes up to 4s, rubidium goes up to 5s, cesium is 6s. If we had francium on this little chart here, francium would be a 7s. That means that francium has 7 energy levels, 7 different shells that it has to go out with electrons in it. But hydrogen only has 1. So it makes sense that the atoms get bigger as you go down the groups. Now, as we go across, why would the atoms get smaller is not so intuitive, but there still is a really good reason. Okay, so the atomic radius gets smaller as you go across the periodic table because each of these atoms has more and more protons in its nucleus. Right? Lithium is number 3 on the periodic table, so that means it only has 3 protons. But neon, on the other end of that same period, has 10 protons in its nucleus. And remember, protons are positive, electrons are negative, so that means that the positives are going to attract the negatives. The protons are going to attract the electrons even more if there's more protons. So lithium and neon have the same number of energy levels. They have the same number of shells around the outside, right? They're both in the second energy level. So lithium has a second energy level, neon has a second energy level, but neon's second energy level is going to be squeezed in tighter because those electrons get pulled in by the 10 protons, where lithium's don't get pulled as far because it only has 3 protons. So as you go across, right, the number of those protons increases. The official way that we would say that in chemistry, right, is we would say that the effective nuclear charge increases. Because the nuclear charge would be the protons in the nucleus, and effective simply means how much pull they have. So the effective nuclear charge is increasing because you have more and more protons. Now, there is another trend that would be ionic radii. Ionic radii simply refers to atoms that have gained or lost electrons. That's what we call ions, if you remember that. So ions are atoms that have gained or lost electrons. So the metals on the left side of the periodic table, they tend to lose electrons and become positive. The nonmetals on the right side of the periodic table, they tend to gain electrons and they become negative. As you go across, ionic size, the ionic radius, decreases as you go across the periodic table. It increases as you go down. And again, why? Well, it's really the same exact reasons as to why atomic radius decreases as you go across and increases as you go down. As you go across, you have more and more protons in the nucleus, right? You have a greater effective nuclear charge. And as you go down, you still have more and more of those energy levels, those shells, okay? So both of these trends are basically one and the same. So it's easy to remember them, because if you remember one, you remember the other. Now, there is another property that we talk about on the periodic table called ionization energy. Right? Ionization energy is the amount of energy needed to remove an electron from an atom. So you can imagine that it's going to take energy to remove an electron. Let me just draw a quick little sketch here. So the middle of the atom is the nucleus. We have a positive charge for the nucleus because that's where the protons are. And then we have these energy levels going around the outside, right? Each of these energy levels, I don't know where that comes from. Each of these energy levels is going to have electrons on it, right? And so imagine if you had an electron here on the third energy level. It's being held on by the fact that it's attracted to the positives in the nucleus, right? There's a negative electron here. It's attracted to the positive in the nucleus. Well, if you wanted to come by and take this electron off, you're going to have to really pull at it because it's being held on by this. It'd be no different than if some, huge supernatural being floated through space and wanted to come and take our moon away from Earth. Well, why is the moon here in the first place? Because Earth's gravity is holding it on. So it would take some amount of energy to pull it away. So same thing, there would be some amount of energy that would be needed to remove that electron. That's what we call ionization energy. Now, ionization energy, as you can see on the little chart here, it increases as you go across, and then it decreases as you go down. I always like to think of things going down the periodic table instead of up, like this shows. So as you go down, it decreases, and as you go across, it increases. Now, why is that? Again, it's important that we know why that is. So, ionization energy increases as you go across the periods. Why? Because again, you have more of those protons. The protons are holding those electrons on. The more protons you have, the stronger the attraction is for those electrons, and therefore the more energy is needed to remove them. So it gets really difficult to remove electrons over here, right? But it's not so bad over here. Francium in this corner here has 7 energy levels. So that means that its outer electron is on the 7th energy level, way far away from the nucleus. It wouldn't be so hard to remove that. So when we go down the groups, the ionization energy decreases down the group because each period has more and more energy levels. Once again, we use that same reasoning. So francium has 7 energy levels. Hydrogen only has 1 energy level. So if you wanted to take away an electron from hydrogen, hydrogen's is going to be right here next to the nucleus. It's really going to be held on tight. But francium's is going to be way out on the 7th energy level. And there's not going to be much of a pull onto that electron. Therefore, it's going to be easier to remove. So ionization energy increases as you go across. It decreases as you go down. And you need to know the reasons why. All right, last trend is a property we call electronegativity. So electronegativity is a really long word, but it has a really simple meaning. Electronegativity is the ability of an atom to attract electrons in a bond. So if you have an atom that's bonded with another atom, and let's say they're sharing their electrons, and we're going to talk a lot about this when we get into the further chapters here. But when we have two atoms that are sharing their electrons, one of the atoms may be more electronegative, which means they would like to attract the electrons even more. Now, I want you to think about this. What would attract electrons? Well, the only thing out there that would attract a negative electron would be a positive proton. So things that have protons, a lot of them, are going to be better at attracting the electrons, right? Or if the protons are not covered by a whole bunch of energy levels, that would also make it easier. So you notice the trend. The trend is as you go across the periodic table, electronegativity increases, and as you go down, it decreases, which is the same trend as ionization energy. The reasons why are pretty similar to what we've been just talking about. Electronegativity increases across a period because the elements are closer and closer to getting a very full energy level. Okay, we're going to describe this later on as an octet of valence electrons. But for now, the important things to realize is we know that all of the group 18 noble gases are all at the end of their energy levels, right? Like helium has a completely full first energy level. It's 1s2. Neon, which is right below it, neon is in the second energy level. It ends at 2p6. So it has completely filled the second energy level at 2p6. And as you go down through all of those noble gases, they all have a completely filled energy level, which makes them very stable. Well, all of the other atoms that are on the periodic table all want to be like that. They want to be nice and stable like the noble gases. And if you're in this group, let's say group 17, right next to them, you almost have a full shell. You have a full energy level. Almost. You're really close. And so you really want electrons. And therefore, you're going to pull on those as hard as you can so that you can get what you want, which is to be like the noble gases. But if you were over here, let's say in group 1, if you're in group 1, what are you? The alkali metals, right? You're the alkali metals. Alkali metals only have one electron in their outer energy level, right? So if you're lithium, you're 2s1, right? Or if you're sodium, you're 3s1. Or if you're potassium, you're 4s1. You only have one electron in your outer energy level. If you wanted to be like a noble gas, you're going to have to gain a lot more electrons. And that would be really hard to do. So they're not very electronegative. And then the other part of this is going down. Why does the electronegativity of an atom decrease as you go down? Well, it's simply because you're further and further away from the nucleus at this point. If you're hydrogen up here at the top, you're trying to attract an electron into the first energy level, which is right next to the nucleus. That's not so far. But if you're francium, are you going to attract an electron in your 7th energy level, way out there, way beyond the pull of the protons, or at least not much of a pull from the protons? Not going to be able to do it. Okay? So this is what we're talking about. When we talk about electronegativity, and this is going to be really important in the next couple of chapters, chapters 7 and 8, we talk about electronegativity quite often. You need to know not only what is the trend, so it increases as you go across, it decreases as you go down, but you need to know why that is. That's going to become very important. Okay? Well, that's it for chapter 6. Next stop, we've got homework due and notes quiz and tests coming up.